Welcome everyone. Let's review what we have learned so far. So, this is a typical neural network. It will have some inputs. This is the input level, basically, the input layer from entire this entire thing is the input layer. Along with that, it will have some hidden layer as over here. Okay, this is the input layer, then there's the hidden layer, and there's the output layer. Okay, so inside of those layers will be some neurons. So in input layer you have this 1, 2 and 3 neurons. For hidden layer you have these 2 neurons, and then the final output layer has 1 neuron. Okay, so what else did we study? Inside those neurons we have our SOP, that is the sum of products. Along with that, we do have our activation functions. Okay, so activation functions are ReLU. We have seen ReLU, we have seen softmax. Okay, so this is the way ReLU is represented, and this is the way softmax is represented. Sorry, sigmoid is represented, not softmax. I'm so sorry. Sigmoid is represented. Okay, then we have our y hat, which is the output, x1, x2, x3, which are the inputs, and the associated weights w1, w2, w3. Okay, so I guess this covers all the components of a normal neural network. I forgot these two, that is loss function and optimization function. So once you have your output ready, okay, so what do we do with the output? We calculate the loss, which is y minus y hat. Okay, this is a loss. If you have multiple inputs, as we have over here, okay, so in this case, the loss function, if we use mean squared error, so r will be 1 by 3. This is 1 by n. So basically the error will be 1 by n summation of I equal to 1 to n 1 to n I is equal to 1 to n, and then y minus y hat. Okay, yi minus y hat I. Alright, and that's the summation. So this will become as equal to 1 by 3 into yi, that is y1 minus y1 hat, and this plus y2 minus y2 hat, this is the second one, and plus y3 minus y3 hat. Okay, and this will be the loss function for mean squared error. Okay, mean squared error, MSE. Okay, but that will be if we decide that we are going to apply it after all the entire epoch. Okay, so we first find out the values for x1, w1 and such, then we find out the value for the second input, then we find out for the values for this third input, and after the entire epoch, what we do is we basically have our idea. Okay, that is for NOT gate. I'm sorry, this one is not applicable over here. It is for NOT gate. Okay, NOT gate that we saw in the video that we saw. What we did was we gave it was a network like this, right? A simple network. Okay, so one input at a time was given, and so what we did was we processed the first input, and then we calculated the loss function. Okay, so if we don't want to do that, what we can do is we can process both the inputs at once and then calculate the error by this way. All right, and then use then calculate uh, the error. Okay, so that's about the loss function. Now we come to the optimization algorithm. Optimization, as we have seen, there's Adam optimizer, which is very famous. ADAM. Okay, and there's different optimization algorithms. I guess gradient optimization is also present. Okay, so these help in reduce the losses of our model. Okay, and those are all the basic components of our neural network. Okay, these are the components of our artificial neural network. Okay, let us move on to the next module uh, on the key concepts of model evaluation. Okay, so underfitting is one of the concepts of model evaluation. Underfitting is when the model is too simple and does not capture the underlying pattern. Okay, the symptoms are it has high training error, but high validation error, but the model performs poorly on unseen data. Okay, so when you created the model in such a way that it performs very well on the data that it knows, and performs very poorly on data that it does not know, that is where you have underfitting. The causes is a model lacks complexity, insufficient training or data or time, and poor feature engineering or missing important features. Okay, overfitting is the opposite of underfitting, where the model learns each and every uh, input in such a way that it also learns the noise which it should not have done. Okay, the symptoms are low training error and high validation error. Okay, so the model fails to generalize. All right, we don't want a too complicated network, and we don't want a model which will not be fitting on even the simplest of the datas. All right, so what we want is a model in between. All right, causes is the model is overly complex, it has insufficient training data or lacks data augmentation, and lack of regularization. So the bias and balancing the bias and the variance. This blue line represents the bias. Bias is some preconceived notion of the data. Okay, so it is oversimplistic assumption of the model. It leads to underfitting. Okay, so bias is we usually say the a person is biased in favor of or in against, right? So if a person is biased, that basically means that person has a preconceived notion of something. Okay, say bias in favor of or bias against, and uh, that basically hampers the learning. All right, variance is high sensitivity to small fluctuations in training data. So basically it the model gives greater than normal importance to any feature, each and every feature, and that's variance. Okay, that is shown by this green line. The error goes on increasing in variance if more and more data as more and more data occurs. Okay, and we have to find such a balance in such a way where the there's no bias error and the variance error are minimal. All right, so that sweet spot is called as the bias variance trade-off, and basically that is where our data is our model is performing at a very good uh, rate. Okay, the goal is to achieve a balance between bias and variance to improve generalization. Okay, Then the classification metrics, there are these four metrics for classification: accuracy, precision, recall, and F1 score. Each of them have their formulas. Uh, Accuracy is the portion of correctly predicted instances, so that's correct predictions upon total predictions. Precision is the fraction of true positive predictions of all the positive predictions. Recall is sensitivity, that is a prediction fraction of positive predictions out of all the actual positive cases. F1 score is harmonic mean of precision and recall. Harmonic mean is the type of average that emphasizes smaller values. All right. Regression metrics. So as we know there are classification type problems and regression type problems. Classification is basically where we have discrete classes. You may have number of classes. It might be two classes or it might be 1,000 classes, but they are discrete. Okay. Regression is where you have continuous values for the output. Okay. So in classification, outputs are discrete, either 1 or 100 or 1,000, how many ever you want, but they are discrete. In regression, it's a continuous output, that is 0.11 to 10,000, whatever. All right. uh, a mean squared error, mean squared error, mean absolute error, r squared, and R2 score. These are all the regression metrics. You can see the formula that we just saw for mean squared error is written over here: 1 by n summation of I from 1 to n y minus yi whole square. I am so sorry, we forgot the square. Mean squared error, we what we actually calculated was mean absolute error then. All right. So mean square error should have been there, but we calculated the mean absolute error anyway. R2 score is given by this formula. Then there is the validation techniques. The train test split. Usually, training and testing sets are divided as 80 to 20 in 80 to 20 ratio. Uh, this may lead to variance in results depending on the split. Okay. Cross validation is when you have less of data, then you use the same data by dividing it into subsets based on random sampling. Okay. So what you do is you use the same subsets, same data, but the subsets are different. Okay. So for example, if we have 10 samples, so if we go by 80-20 split, for the first time the first 80 samples will be training, and the second uh, rest of them will be 80, rest 20% will be for testing. Then again for the same data set, last 80% and the last 80% will be training, and second first 20% will be testing, and so on. Okay. So that is cross validation. Leave one out, cross validation, sorry. It's a special case of cross validation where k equals the number of data points, computationally expensive but very highly accurate. Okay. Regularization, to improve evaluation. What regularization means is, as we saw just now, uh, introducing variance. Okay. Variance is where you where the model learns each and every data set as if it was very important. Okay. And that should be reduced. So that is reduced by regularization techniques. There are three regularization techniques: L1, L2, and L3. L1 is called as lasso, L2 is ridge, and the third one, sorry, it was not L3, it is elastic net. Okay. L1 is has this formula, L2 has this formula, and L3 combines L1 and L2 penalties. Okay. So the loss is our error plus lambda into uh, W of I. Lambda is the learning rate, and W of I in case of L1, and Wi square in case of L2, and addition of both. So with that we come to the end of this lecture. Let's meet in another lecture. Thank you.